All right. I guess Malar and I we'll go kick it off. Thanks everybody for joining.
Fraser, I'll just take a couple of minutes to introduce ECSPrecip and then we can
start. Sure. Okay. Sorry.
I'm sorry. Okay.
No, that's totally fine.
So hello everyone. Thank you for joining us today. I'm Shruti Upadhyaya. I am chair of Students and Early Career Subcommittee of AGU's Hydrology Section's Precipitation Technical Committee, and we call ourselves ECSPrecip. So like I said, before we move to seminar, I'll take just a couple of minutes to introduce ourselves. Here is ECSPrecip. We try to bring in young scientists interested in different aspects of precipitation related research with a goal to better connect with students and early career scientists in the domain and providing them opportunities for networking, professional development, and recognition. So ECSPrecip subcommittee is striving to facilitate an open, inclusive, and collaborative environment for students and young scientists in the field. So this year we started two series of bi-weekly newsletters called Precip Folks and Science Highlights. This is with an intention of providing more visibility and recognition to students and early careers in the field. I'll put links to these in the chat soon. This year, as you already know, we started this new quarterly seminar series. First seminar, which was organized in June, was dedicated to early career speakers. And today we have three amazing speakers who are experts in different aspects of precipitation related research. They will be discussing the challenges and issues with operational precipitation products, which are commonly used in research. So with this, I would like to thank you again for joining and mention that this session will be recorded and will be posted on our website. Now I will hand over remaining session to our moderators, Malar and Fraser. Fraser, you can take over from here.
Yeah, sorry, thanks for the intro. All right, yeah, so we have some exciting talks today. And I think we're going to start with Jackson and work our way through, and we're going to be taking questions both in the chat, and I think if you want to ask as well, just using your voice, you can do so. So feel free. Malai, did you have anything you wanted to add before we jump into things here?
Okay, I just want to say we're going to have three speakers today. Each are going to talk for 15 minutes. And after they talk, we're going to take all the questions. So as you think of questions, just put it in the chat and we will do that in the last 15 minutes. Yeah, let's go ahead with the first speaker.
All right. So our first speaker today is Dr. Jackson Tan. Jackson is an associate research scientist at the University of Maryland, Baltimore County, working on the GPM mission and iMerge precipitation algorithm at NASA Goddard. His research focuses on include MODIS, ISCCP cloud regimes, the relationship between clouds precipitation, and ground validation of satellite precipitation. He received his PhD in atmospheric sciences from the Monash University in Australia in 2014. And today, Jackson's going to be talking about an overview of satellite precipitation products. So I'll pass it over to you, Jackson.
All right, okay, thank you very much. And I assume you can see my slides. So I'm going to go ahead and I'm going to talk about satellite precipitation products. Which, if you go to Google, you type satellite precipitation, you can grab the products. But what I want to do here is try and give you a sense of the different ingredients that go into the creation of these products and what is being done to, process and derive them. So, there's all these satellites out there which are capable of measuring or estimating precipitation signal. So how do we get from that to the precipitation estimate? So I'm going to talk about the retrieval process, whether it's active or passive and what sort of frequency it uses and what sort of orbit that the satellite is on, and then the processing that goes on behind the scenes. And then, with individual satellites, that's all and good, but people like to have gridded products, and so you have to think about how you merge all these satellite observations. And then finally, I'll give a few hints or tips about selecting a precipitation product that best suits your need, not just for satellite, but also compared to the other two topics that we're going to talk about, which is few experiments and models. So the first thing to consider, the first property of satellite retrievals that is very important is whether it's an active or a passive instrument. So an active instrument, as you can see from the animation, is when it sends a beam of signal and it measures what the reflected signal is. And so this is active and is generally more accurate because it gives a lot of, it's able to sample the entire atmospheric column and it provides more information. So examples of active retrieval instruments are the GPM DPR, the GPM radar, the TRIM radar, and also the CloudSat CPR radar. On the other hand, you have passive sensors, which is, which is like a camera without the flash. So all it does is that it measures the radiation that comes out from the Earth. Because it's simpler, there's a wider swath, and then there are more instruments in orbit with passive instruments. So for examples are the GPM GMI and also the GOES geostationary satellite instruments. And then one other important property is the wavelength that we're looking at, or the frequency. So if you know your physics, you know that any object with a temperature above 0 will emit radiation over a range of wavelength that is dependent on its temperature and emissivity. So for example, over at the bottom there, you can see that the sun emits radiation that peaks around the visible range. I think that the curve is a little bit off, but over visible, a little bit over ultraviolet and infrared, whereas the Earth emits predominantly over the infrared region, although because the curve has a very long tail, so over a microwave, there is some emission as well. But this radiation is also scattered. It's scattered by particles with diameters that are similar to or larger than the wavelength. So if you have something, say, in the microwave range, it will scatter anything to the left of it. So for example, if you consider microwave, we generally like to use microwave for precipitation observations because it is of the wavelength is about the size of precipitation droplets. So precipitation droplets scatter microwave, but it is because, when there's precipitation, there's clouds. But because cloud droplets are much smaller than the wavelength of microwave, so the cloud droplet do not scatter microwave. So that's why it can penetrate the cloud, as is usually usually characterized as, and measure the precipitation itself. Although in reality, it is a little bit more complicated because the precipitation particles itself emit microwave radiation. And in general, over the ocean, because the background is cool, we rely on the emission signal of the precipitation at low microwave frequencies. And over the land, we rely on the scattering signal of the precipitation over land. And then there is, of course, infrared and visible, which is at much smaller wavelengths. They are scattered by the cloud particles. They are also scattered by the precipitation particles, but usually where there's precipitation, there's clouds. So what this means is that when we use IR and visible, what we are looking at is the cloud information, and we're using the cloud information to infer the precipitation at the surface. And one interesting twist here is that for visible, it is only available during sunlit hours because most of the radiation comes from the reflection from the sun's radiation. So the fact that it's only sunlit makes it hard to deal with when it comes to precipitation. And then another feature that you should consider is the orbit of the satellite. So low Earth orbit, which is about 400 kilometers, is much closer to the Earth's surface, so it provides better resolution. Whereas geosynchronous orbit is high up at about 36,000 kilometers, and it sits at the point that allows constant monitoring. So it can look over one sector of the Earth all the time. And so I like to put this animation. Hopefully you can see it. Now you see this animation of this cloud. This cloud is observed using sensors on board a geostationary orbit. So it can continuously monitor this cloud, the evolution of this cloud over this area. And then you see this satellite just flew over. That's the GPM satellite. It is on a low Earth orbit. So you notice that when when it flies over, the animation sort of pauses in time, so you can take a snapshot of it, but that's all what a low Earth orbit sensor does. It can only take a snapshot and then it flies off to somewhere else. So that's the difference. Now, as it turns out, the orbit it is in is affected by the wavelength of the sensor, because the footprint resolution, if the wavelength is large, the footprint will have a large resolution. So therefore, there's usually a connection between the wavelength and the orbit the sensor is in. And in general, for visible and IR, they are both on geostationary orbit and low Earth orbit with resolutions reaching about 1 kilometer or even 100 kilometers if it's at 100 meters if it's at the low Earth orbit. Whereas for a microwave sensor, it is only available in low Earth orbits, and even so, it has a resolution of about kilometers up to 10, or more often than not, 10 kilometers. It is possible to improve this resolution with complex antenna configuration, but you're talking about satellites which needs to be launched into orbit, so there are a lot of complications involved. And so with all these properties, we can talk about the data processing. And this is one thing that I want to stress over here. Okay, satellites do not measure precipitation. What satellites measure is the electrical signal that is being emitted and reflected, or the radiation. You can even say that it measures brightness temperature, but it doesn't measure precipitation. But of course, some of you may say that, hey, Jackson, what about this? Like GPM, that's global precipitation measurement. Yeah, so I think that, there are reasons for, I think, calling the GPM mission with the word measurement. But in general, I still want to stress that satellites do not measure precipitation. If you want to know more, I can elaborate in the Q&A. Okay, so in general, from the satellite, it measures electrical signal, it measures radiation. How do you convert that to precipitation products? Well, so it depends on all the properties I talked about earlier. Different properties have different algorithms to convert them to precipitation rates. And then one thing you want to do is to make sure that they're intercalibrated with each other, so that if they look at the same system with the same properties, they produce similar results. So calibration is important, and then how you combine the observation from different satellites is also another factor that you need to consider, as well as filling in the gaps, because people like to have regular satellite estimates, whereas if the satellites are on low Earth orbit, the sampling is very intermittent, and also quality control. So on these aspects, I'll talk about it in a moment. But I just want to point out, before I move on, that the choices to decide all these factors is guided by the design priority of the product. So what does the product prioritize? One often underappreciated priority is whether the precipitation product is a climate data record, which means you can use it to look at trends because it has a consistency is a priority over the entire record. Or does it provide the best estimate at any one time, also called the high resolution precipitation product? It's not, sometimes you can have both, but more often than not, it's a trade-off between one or the other. Okay, so moving on. So this is a GPM satellite. It provides you with an observation only at a narrow location, and then you can look at other satellites which can observe precipitation. Well, not too bad, but you notice that there are gaps in between, and there are grooves, and it's sort of still very intermittent, and there are gaps in between. So one thing we like to do, users like, is a consistent product in which we merge everything and interpolate them together. And this is what I'm going to talk about next, which is how we merge the precipitation estimates from different satellites and put them onto a consistent gridded product with a regular interval. And I'll use iMerge to illustrate this, partly because I'm familiar with iMerge, and I'm with the algorithm team, but also, here we go. Also, other gridded satellite products are produced using the broad steps that are used by iMerge itself, or they use subsets of these steps that's used by iMerge. And so what are the steps? Well, first of all, you grid the microwave estimates to find enough resolution, and then calibrate them to a reference product. So now that you got a gridded microwave product, you apply something called morphing or interpolation, and then you bring in precipitation estimates from infrared, and then finally you perform a gauge adjustment. So that's how you get from individual satellites to a complete picture. So first of all, one important aspect is to intercalibrate the microwave. Now, the fact that different satellite sensors have different characteristics, different wavelengths, different orbits and stuff like that means that their precipitation estimates, even if they use calibrated inputs and a consistent algorithm, they're going to have different distributions, and therefore they're going to look at the scene and produce different precipitation estimates. So we want to calibrate the microwave to the best estimate, and in this case, the best estimate is the combined retrieval, the combined observations from both the radar and the GMI. So the idea here is to calibrate the microwave to this best satellite precipitation product that we have. But I just want to point out, I'm not going to go into the details, but I just want to point out here that the calibration is a delicate balance between having a long enough record. If you have a long enough record, you can build a large sample size such that you can have a calibration curve which is very stable and not variable. But at the same time, if you have a long record, you want a record that is short so that it represents the current condition. So, when you do the calibration, you have to take into account the balance between these two factors. And then morphing, the concept is very simple. Imagine if you got a satellite flies over this place and sees a precipitation block 8:30 over right there. And then at 10:30, the satellite flies over again, and another satellite flies over again, and you see that the precipitation has moved over there. Then you know that in the intermediate intervening half hours, at 9 or 9:30, the precipitation is right there. Visually, you can see that. And of course, what's difficult is trying to convert this into implement this in an algorithm. And so in iMerge, I'm not going to go into the details, but we have implemented this. And so you can do this globally everywhere to get a propagated precipitation. And then we bring in the IR precipitation. And then we merge them using inverse error. If they are poorer, we give them a lower weight. If they're better, we give them a higher weight to get a global precipitation product that looks like this. So this is an animation that shows global precipitation product at 0.1 degree every half hour globally. Okay, and I'm not going to talk too much about this. If you want to know more details, you can Google GPM and you can find out more about this iMerge product. So, what satellite product should you use? What are the considerations? I think the question you have to ask yourself is, what are your requirements for the satellite product? Do you need high resolution? What is your high resolution? What is your resolution that you require? What coverage do you need? What about your latency? What sort of latency do you need? And also another consideration is, what sort of precipitation observations do you need? Do you need vertical profiles? If so, if you need a vertical profile, you're only limited to active retrievals. And how accurate do they need to be for your purpose? And I mentioned about climate data records, like whether it's consistent over climate scales. This is important if you're looking at trends. So if you're looking at trends, whether it's a climate data record or not, is an important factor you have to consider. And also whether your observations, do you mind it being combined with models? There are products out there that take the satellite observations and merge them with models to give you the best of both worlds. So is that acceptable to your applications? And okay, I'm going to assume that these slides will be posted somewhere. So there are websites somewhere out there that sort of consolidates. It's not updated very well, but they sort of list different satellite precipitation products out there that you can look at try and compare with each other. So they provide maybe a first guide to, if you want to consider multiple satellite precipitation products, those websites are good. And then I just want to throw out there that when you download a satellite product, you have to remember the difference between whether you're downloading it from a data provider or third-party host. And as an algorithm developer, we only vouch for data provider. If you get from a third-party host, that's your problem. Like if something goes wrong, that's your problem. And I'm just going to quickly talk about how satellite compares with like field experiments. So compared to field experiments, satellite products obviously have wider coverage because it can go global. It has a longer record because it's not focused on a single period, and it is configured to give timely data with low latency. Few experiments can do that, but they often are not. But the drawback is that few experiments are very highly accurate and they have high resolution and provide a lot of information, which satellites, in contrast, do not have. And then as compared to models, currently, right now, satellites have better resolution plus coverage. Notice I say plus because models can have global coverage, but not very good resolution, or you can have regional coverage and very high resolution, but only regional coverage. And satellite generally, compared to models, is better in convective environments, but poorer in stratiform, or similar or poorer in stratiform environments. But the drawbacks for satellite compared to model is that it has a shorter record, and above all, this is the key advantage of models, is that there are no forecast data in satellite products, in observations for the matter, of course. So in summary, I talk about the retrieval process, which affects the information content. And then, whether it's looking at precipitation or clouds, the satellite platform affects the resolution and sampling and how you get from measurement to precipitation. And then how you merge everything, I use iMerge as an illustration of how merging can be done, and usually other products take different subsets or variations of it. And then this is my last point, which is I talked about how you select it. You have to keep in mind your own requirements and how it compares with few experiments and models. And so I'm going to stop here.
Awesome. Thanks, Jackson. I think I always learn something new from your talks. I love the visuals you include. They're great. So I think we'll do all questions at the end. Like we said, again, just a reminder, please post them in chat if you have them as we move along here. So our next speaker today is Dr. Brenda Dolan. Brenda's interests include radar analyses and algorithms, observational integration and validation of cloud resolving models, precipitation processes, and cloud physics. She's an expert in polarimetric radar, having developed one of the first ever hydrometeor identifier algorithms for shortwave wavelength radars, X and C-band. Additionally, she's worked with a wide variety of radars around the world, including ground, ship, and satellite-based radars from Ka to S-band. Brenda has participated in over 10 field projects as a radar scientist or mission scientist. She has worked with large data sets, including from radar and disdrometer. Finally, she works at the interface of cloud resolving models and observations, using them synergistically to improve observational retrievals and better model representation of physical processes. Recently, she has collaborated to develop a polarimetric radar forward operator, which can be used with cloud resolving models such as WRF and RAMS. Everybody, here's Brenda. Thank you.
Thank you for that introduction. And actually that sets me up nicely for what I'm going to talk about today, which is precipitation data from field projects. And actually I appreciate going after Jackson because, let me see if I can get my computer to obey me. I want to kind of motivate this with why are field projects important for observations of precipitation. As we just saw from Jackson, we get this global view of precipitation products from satellites. A lot of countries have really nice operational radar networks. There's mesonets, so what is the role of field projects? Well, it's to intensely observe interesting or critical or missing or remote locations. And obviously the most, the biggest one is over the ocean. We don't have measurements over the ocean from the ground to help validate those satellite observations. And of course, the Earth is mostly, ocean where we don't have these observations. So for field projects, we can deploy instruments to meet specific scientific goals. But that really, we get these great observations, but there's challenges that come along with that, because typically these are very short time periods, on the order of weeks to a couple of months usually. They end up being sort of discontinuous in space and time. And so this middle figure here is showing where we've deployed our seagoing radar. And so over different years, we were sort of in different parts of the Pacific Ocean. You can have instrument issues and data problems where you have just an instrument doesn't work on one of the days that you're really hoping to get some data. You have different operational characteristics across these different projects. You can have different data formats. All of the different PIs have different goals, and all of these different field project data live in different places, which I'm going to touch on in a minute here. So because I am a radar scientist, I'm going to kind of focus on that. But so we have deployable precipitation radars at X, C, and S band, is what I mean by precipitation. And that kind of plays into what Jackson was talking about the wavelength that you're transmitting at, and what you can see from those radars. So we're really looking at precipitation size targets with X, C, and S band. So we have NCAR's S-pole radar, we have NASA's N-pole radar, these are S-band. We have CSU's C-band seagoing radar. There's a variety of DOE radars that are X and shorter wavelengths. There's, of course, the DOWs and the SMART-R and the NOAA-XP and D3R. Some of these are into the cloud and millimeter wavelengths, sub W, Ka, and Ku. We have airborne radars such as the APR-3. We have the HIRAP, which is some of these shorter wavelength radars as well. There's vertically pointing radars, and then there's continuous wave MRRs, which is micro rain radars. That's what's being shown here. And a lot of these, well, all of these radars give you reflectivity. And if you have a polarimetric radar, then you'll get other moments such as differential reflectivity or specific differential phase. And if it's a Doppler radar, then you get Doppler velocity. So sort of similar to what Jackson was highlighting, these are derived quantities though, and I'm going to talk a little bit about that in a minute here. But some of the advantages of using radars are that you get rainfall or snowfall over a large coverage area. We're talking about thousands of kilometers squared at high spatial resolutions on the order of 1 kilometer and relatively high temporal resolutions, you know, on the order of, 5 minutes to 20 minutes. And sometimes, you can really get at the microphysics in the clouds depending on how your radar is scanning. And so you can derive properties like the hydrometeor identification or properties of the size distribution. Some of the cons of this, though, as I mentioned, these products are all derived. We're really not measuring rainfall. We're measuring reflectivity, which we're converting to a rainfall. You have to consider the data quality and calibration. Those are really important if you're going to derive things like rainfall. You have to consider things like beam blockage, attenuation, particularly as the wavelength decreases or shortens. And sometimes the radar has a hard time deciding what the phase of precipitation is. And based on sort of what the objectives of the field campaign are, you can have different scanning strategies. So the heartbeat is what kind of like the revisit time. And these can range from 6 to 10 to 12 to 15 to 20 or 30 minutes. You can set the radar up to scan different ways. So you can have PPI volumes, which is where you go 360 at different elevation angles. And that's really good for if you want to map something like rain, and it gives you widespread coverage. But the RHIs, which are high resolution vertical slices, really give you much more information about processes and microphysics happening in the cloud. And so as you start mixing these up, then you can get longer heartbeats, longer revisit times, but different information. So as I mentioned, we're really deriving the rainfall and some of these characteristics from our measurements of the radar. And what's being shown in this image here is the relationship between rain and reflectivity, and which we usually assume is a power law, Z equals AR to the B. And this is just a scatter plot of different prefactors and exponents that people have found in rain. So there's not this one-to-one correlation. If we have a polarimetric radar, we can use estimators like specific differential phase or ZDR, which help us really kind of narrow down this broad spectrum here. And a lot of people have gone towards blended algorithms where you select a different estimator based on what you're actually looking at and the quality of the measurements that you're making. And some of these relationships actually depend on your location. And so we derive these relationships from other instruments such as disdrometers. So as you kind of see all this come together, hopefully you're sort of starting to think about what the uncertainty and errors are in such a measurement from radar. And of course, you need to consider about where this is happening. Where are you able to derive these quantities? Is it at the lowest radar level? So as the Earth curves under the beam, you're looking higher and higher in the atmosphere. So a lot of people grid their data to some level, and of course your scanning strategy is going to dictate what that lowest gridded height that you're able to get data at. I also want to touch a little bit on disdrometers and in situ measurements of some precipitation quantities. So you can put out things like pluvios, which are weighing gauges, disdrometers like parsivals, 2D video disdrometers, or even just rain gauges and tipping buckets to tell you how much it's rained. And then you can put some of these probes on aircrafts or balloons. So this is called the high vis, and it's a video disdrometer that the Japanese attached to a balloon and then let go into the clouds. And in these cases, the measurements are giving you particle size distributions, fall speeds, number concentrations, and axis ratios, which then you can use to get at derived quantities such as rainfall and liquid water contents. So the pros of things like disdrometers and particle probes are that they're giving you size distributions, and you can integrate them to get a precipitation amount. They're at very high temporal resolution, on the order of 30 seconds to maybe 3 minutes. But there are some cons to consider here as well, such as quality control. If you have wind influences on how those drops are falling through or blowing through your captured area, splashing off the side of these metal things can influence your retrieved or your measured drop size distribution. Of course, you have to consider what the measurement parameters of the instrument are. Are they really able to see the small drops or even the large particles like hail? And they're really just point measurements, right? So the catchment area of this is like 30, well, I think 10 centimeters squared. And so really, that gets at the variability of precipitation. If you put two of these next to each other, are they really going to be measuring the same thing? And how does that relate to your model grid box or even your satellite footprint? And I just wanted to mention the ocean rain data set. So this is a really cool set of data where they put optical disdrometers on ships, essentially research ships that sail around the world. And these are mounted freely to turn with the winds. And so they have snow and rain measurements with this. And they've included environmental characteristics as well. So like sea surface temperature, winds, you can get things like the ceiling. So you can really kind of look at over the oceans, some of these quantities, which is really amazing over like a 10-year period, I think. So how do you access all of this data? It really kind of depends on who funded the project, honestly. A lot of the data from the DOE is hosted on the ARM Discovery tool, which is actually a really nice tool for visualizing data. You could just go to this webpage. You can look up data by field project type, location, or even the measurement that you want to get out of it. You can pick up the data in a variety of formats from Globus or wget threads. They give you different versions of the data, which I'm going to talk about in a minute, whether you want raw, QC, moments, products, or PI products. As you download the data, it gives you a README file and a data quality file that tells you, if they think there's some untrustworthy data in there. It's all version controlled, and they provide the citation and the DOIs with that. NASA has a similar website where they host a lot of data from field projects. You can usually get the QC data is what's available. They also provide README files and citations and DOIs associated with the data sets. And typically this is kind of like an HTTPS where you kind of click on each file and you can download that. NSF stuff is typically archived on EOL's field project catalog, and they just have tons of experiments here. And you can just go through and click data access, whichever field project you want. It also includes citations, and you can download it via FTP or OpenDAP. And then I just put the link here for Ocean Rain Data Set, which is hosted in Germany. And they provide this QC data for about 10 years from 2011 to 2020. So what does the data look like when you get it? Well, there's a couple different levels of radar data. So level 2 is when you have corrected radial data, which is when you have it in gate format, which is azimuth, elevation, and range. These are typically CF radio files that are NetCDF compliant. You can use tools like LROS or PyArt to look at these, process the data, and you get the radar moments here to look at. Sometimes these will include rain rate or hydrometeor identification, particle ID, but typically those come into level 3, which are the products. And this is typically gridded. And these are NetCDF files, and they include the best estimate of rain rate or hydrometeor identification, sometimes a calculated DSD. Disdrometer files are typically either text files or NetCDF files that include the bin data, so that's the number of drops per size bin, fall speed, and then you can get the integrated information, which is rain rate and liquid water content, total number of drops, a calculated reflectivity, and sometimes a fit distribution, like a gamma distribution parameter. So in summary, field campaigns are critical for precipitation observations. You can really get detailed and targeted measurements in challenging and data sparse locations. And they provide high resolution spatial and temporal data related to the amounts, types, particles, size distributions of precipitation. But field campaign data can be challenging to work with due to complexities of the instruments, the locations, and discontinuities. Data often requires specialized and careful QC and calibration, and a lot of these properties are retrieved quantities, and so you need to think about what are the errors, the uncertainties, how is it calculated, what level am I looking at, and kind of what was the focus of the project with different scanning strategies that provide different opportunities. And with that, I will end.
All right, thank you. That was great. Those links are extremely helpful, so I'll make sure to check those out later, and we'll circulate those as well. Okay, our final speaker today is Dr. Elinor Martin. Elinor is an associate professor in the School of Meteorology at the University of Oklahoma and an OU co-PI of the South Central Climate Adaptation Science Center. The research team she leads aims to understand climate variability and change with a specific focus on precipitation variability across the Americas and tropics.
Okay, thank you very much. It's nice to be here to talk about climate models and not just be with climate model people, because climate models and observations of precipitation go hand in hand. And so this is not some kind of competition between the three of us of which thing is best. They will have their pros and cons. So I'll try and be brief so we have time for questions. But this is just a nice little image kind of trying to symbolize what a climate model grid box looks like and all the different things that are happening inside this 3D climate model grid box. And these might be of order 100 to 200 kilometers in space for one box. So within a 100-kilometer box, we can have multiple clouds, one cloud, we can have rainfall in some parts and not other parts of it. So when we think about precipitation in climate models, it's actually coming from two different components. It's coming from the large scale, essentially, which is the cloud processes at the large scale, 100-kilometer, the size of the grid box, converting cloud condensate to precipitation. And we have the precipitation coming from the parameterizations themselves. And in climate models, there's typically a deep convection parameterization and often a shallow convection parameterization. So this is representing the processes that are happening inside the grid box at less than 100-kilometer scales. And sometimes the large scale is referred to as the stratiform rain and the parameterized is the convective rain. That's not strictly true. There can be stratiform rain within the convective parameterizations, and there could be convective rain in the large scale. So we do see that distinction made, but it's not technically correct. We've heard briefly about cloud resolving models. So I'm just going to mention some of these things really briefly, but I'm going to mainly focus on the large scale climate models. So within cloud resolving models, they're obviously treating all kinds of convection and clouds in a unified framework. So it's not large scale versus parameterization. They're all being treated by the same methods. And usually this is less than 5 kilometer resolution, and this is not common when we're doing large scale climate modeling across the globe, although it has started to happen a little bit. In climate modeling, we do have some models that are variable resolution. So you could have higher resolution over the region you're interested in and lower resolution in other places, or what's called super parameterization, where essentially you put a cloud resolving model within a grid box. But one of the challenges is precipitation is one of the more computationally expensive parameterization. Right? It could be using around 10% of the total cost of building these climate models. So if you can build a better and more efficient parameterization that works at these new scales, then that would be an excellent use of your time and would really benefit the community. So I'm going to focus mainly on what's called CMIP-6, so the Coupled Model Intercomparison Project, Phase 6. And what this is, it's a coordination of model experiments across the globe. So it's trying to do this in a uniform way with a common infrastructure for collecting, organizing, and distributing the output from models. So that makes it really nice because you don't have to go to 27 different modeling websites to get the data, and you don't have to worry about did they use the same forcing, did they use the same boundary conditions, because all of that is prescribed in these experiments. So on the right-hand side, this is an illustration of kind of how these CMIP-6 experiments are set up. The historical simulations are required. That's called DEC in this case, which is a German abbreviation. And then they have all these different types of experiments around the outside. So scenario MIP is for future scenarios, future climate change. If you're interested in land use or carbon cycle or aerosols, they have different types of experiments for focusing on different types of processes. So the CMIP-6 is the most recent generation of models, and it's used in the most recent IPCC report as well. So it includes over 30 climate models, more than 10 of these MIPs, model intercomparison projects. There's hundreds of ensemble members, 100+ experiments, and just petabytes and petabytes and petabytes of data available. There's still data available from CMIP-5, the last one, and CMIP-3. There's no CMIP-4, so that's still available also, and you can access it in almost the same way that I'm going to show you. So the nice thing about this is they have the same variable names for all of their different model simulations, and they have the same structure, and they're all NetCDF, and it makes it much easier than some other situations. So I put the link up here for the variable search tool, so you can go to this website and you can type in different variables and see all the different kinds of variables that the models produce. So I put kind of the main ones here related to precipitation. So of course, the main one is the precipitation flux. It is in a units of flux, so kilograms per meter squared per second. So if you are interested in millimeters per day, you would need to convert that from essentially millimeters per second to millimeters per day. It includes the precipitation from the parameterized convection, as well as the large scale. It includes any phase of precipitation. It's just everything that is precipitating at that particular interval that you've selected. You can also get just the convective precipitation, so the part that's coming from the parameterization. You could get the part just coming from the shallow convection. There's also another variable output called maximum hourly precipitation rate. And you can also get snowfall from the models. So these are some of the more common ones, but there are lots of other ones available. Here's just some of them. I know there's probably people interested in lots of different topics. Sorry. So you can get things like the mass fraction of solid precipitation falling onto surface snow. Seems very specific. Precipitation falling onto vegetation, onto crops. You can get the rainfall specifically rather than the precipitation. You can get precipitation containing certain isotopes, which is important in some of the paleo simulations also, and some more information about snowfall flux. So there's lots of things available, Does that mean that you should use them all and they're all as accurate as each other? No, it doesn't, but they are available. So you can access all the CMIP6 data through the WCRP search interface. There's a user guide available. So this System Grid Federation link on top will essentially take you to this place. You can sign up for an account. It's free. You just have to register. And then there's this nice GitHub that has information about all the different experiments, about the abbreviations used so that you can know what you're getting and what you're using. So I'm just going to illustrate a search using this process. So we're going to click down here on the variable button and look at all of the variables related to precipitation. So most of them start with PR when they're about precipitation. So you can search for them and you can see that for precipitation flux, you get 77,000 different results. So this is different models, different experiments, different time resolutions. It's a lot of data. Snowfall flux is the next most common. Convective precipitation, maximum hourly rate. Some of these other ones, they aren't as commonly output by the models. So knowing what you have available is important when you're thinking about how to answer your questions. So we can also then, if we choose just precipitation flux, we can look at the different time resolutions available from the models. So they're shown here on this side where it says frequency. And then this is the snapshot of what these different things mean. So there's about 143 results that have hourly output from the models. The most common are the daily mean precipitation rates and the monthly mean precipitation rates. There is some output at 3 hourly, 6 hourly resolution, but again, the higher resolution you get, the fewer models you have available because it takes a lot of data storage space to output information at that resolution. It's also important, to make sure you know if it's a mean sample or if it's sampled at that time period. So is it a sample at 0Z or is it an average from 0Z to 3Z? And that is going to make a difference when you're trying to compare and validate your model. So validating model precipitation, it's more than just how much rain was there or what's the climatology. We have to think about the timing of rainfall. We have to think about intensity. Extremes are especially challenging in climate models, mainly because of scales. To think about the frequency, and we also think about the phase, whether it's liquid or solid. Another important thing to remember is that model years do not equal observation years. So climate models are not forecasts. They're not simulating exactly the years that we observed. So if you're interested in 1995, you can't just grab all the 1995 years from the models and compare them to observations. The models are just representations of natural variability within the system. Can you look at trends? Yes. Can you look at climatologies over a period? Yes. But you're not comparing individual events or individual years in models and observations. And another challenge is that precipitation suffers from the effect of error in thermodynamics and the dynamics within the models, because they're all important in the amount, the phase, so on of the precipitation. So there are, of course, errors. A lot of times, I've mentioned this briefly, stakeholders and community partners really don't find 100-kilometer scale precipitation useful to them. So there's a lot of efforts to do what's called downscaling, to take that large 100+ kilometer grid box and make it a higher resolution for people using the data. And there's two different ways to do that. One is statistical and one is dynamical. So through statistical downscaling, you have to have long period of observations to train your statistics. And the downscaling is sensitive to which observational product you use. So it's important that you understand the observations as well as the model precipitation. It also depends on the statistical method you use and the climate model that you downscale, but it's something that can be done relatively cheaply in terms of computation. There's a couple of different examples here of downscale data sets. The South Central Climate Projections Evaluation Project is one that I used that was generated here for the South Central US. And the NASA Global Daily Downscale Projections are also now available. And then there's dynamical downscaling, which uses a regional climate model. Something like WRF, perhaps, may still be parameterizing convection, depending on what scale you're downscaling to. So you can still have similar errors. And CORDEX is the Coordinated Regional Climate Downscaling Experiment for different places across the globe. Depending on where you are based or what region you're interested in, they typically have downscaling, dynamical downscaling for that region. So I will end there, and see there's questions in the chat. So hopefully we can have a nice conversation.
Thanks, Elinor. It was a great talk to sort of finish off our trio here, talking about radar, remote sensing, in situ, and models. So I think we have a few questions, and just again a reminder for all the other people here, please feel free to post your question in the chat. We'd love to hear from you, and I'm sure the speakers would as well.
Yes, I would again like to thank all the speakers. It was amazing to hear from the basics to see how much of effort is being done in each and every product, satellite, ground-based, and model-based products. The amount of work that goes behind, that's been very clearly seen. And with that, let's take some questions in the chat. First question to Jackson. How is the gauge adjustment step performed in iMerge? And what would be a good alternative for GPM in your mind?
Okay, thank you. So how is the gauge adjustment done in iMerge specifically is that, so in iMerge, we do not have the capacity to gather individual gauge observations. So we use a derived gauge product from, I think in this case from GPCC, which is gridded and it's easy for us to use. And so what we do is we use that and we combine sort of that we average with the satellite precipitation in a way that is inversely proportional to the error, the expected error. And then we apply this to every half hour, such that the half hour summed up over the month is scaled in a way that is similar to the gauge. So it's sort of a combination of both. And so what's a good alternative name? So I think GPM is a very good name. We don't want to change that. But obviously the M measurement is a little bit awkward for satellites. And the reason why I mentioned that is that, yes, I think the way I would see it is that GPM is a mission. It's a mission to understand precipitation around the world. It's moving towards measuring precipitation around the world globally. Yes, GPM mission revolves around the GPM core observatory or GPM satellite, but the satellite is not the only thing. We have a lot of other resources like gauges that you just mentioned. So that is one piece of information that goes into it. So I think GPM represents this grand vision to try and measure precipitation, not just using satellites, but with everything. And so that's kind of how I would phrase it. GPM is a good name.
Fraser, you have something to say? Okay, if not, I'll go to the next question. I'm going to skip Shruti's question because it's a good discussion topic that will come to the end. Let's go to Brenda's question. Is there a way to get a list of the ground-based campaigns in one place, or do we need to search in each one to find what we need?
Gosh, that is a great question. And I wish you could just have a database and you type in something and it tells you all of the field experiments. but there's not really, and it really kind of depends on, like I said, who funded the field project. But the big main ones that I would start with, is going to the NASA database, going to the DOE ARM archive, and going to NSF's EOL's site at NCAR. I did just see that NCAR has over 400 field experiments listed. So that might be the best place to start. Kind of search through there and look for ones that are related to precipitation. But yeah, there's not like a, grand unified database. So.
It's good. Next one to Elinor. How reliable is precipitation from models? According to your experience, when do you suggest to use precipitation from climate models compared to satellite and field observations?
Oh, it depends what question you're trying to answer as to what type of data you want to use. Right? Generally, do climate models reproduce our climatology of precipitation globally? Yes, in general, they have some well-known biases, like having kind of a double ITCZ structure. I also do something with my students every year, graduate students. I show them some maps of model climatology and observed climatology and get them to pick which one is real, and usually they can't. So it's reliable enough that visually we might not be able to see climatological differences, but if you're interested in long-term variability, climate models are going to give you more information if you don't have 100 years of precipitation data, for example, that you can't do with field observations or satellite data. If you're interested in the future, you definitely need to be using climate models. But if you're using climate models at all, you can't do them without observations of some kind to understand the biases of the models. So I'm of the mindset that you cannot purely be a modeler and never use observations. You need to understand them both.
Right, that makes sense. And the second question is, what would be the difference between climate models and reanalysis?
Yeah, so reanalyses are trying to reproduce the exact global weather conditions for a given day, right? So they are combining observations and a model to reproduce the conditions on a given day. Climate models aren't trying to reproduce the exact weather on a given day. They're trying to simulate the climate over an extended period. So they have a different purpose. That's why we can't compare exact days in climate models. Because, we can't forecast 50 years in advance, but we can project the climate 50 years in advance because we're interested in the boundary conditions and not the exact weather conditions on that day. So.
Okay. And there's a question for Brenda. As the ship keep moving, how the ocean rain measure precipitation continuously? I mean, isn't it very likely that ocean rain misses a lot of precipitation events?
Yeah, so the answer is yes. It misses a lot of the precipitation events. And I mean, that's actually even true of the ship-borne radars. We're not going to sail into a tropical cyclone. They're going to try to avoid really intense stuff if they can. But at the same measure, a ship moves really slowly. And so you can't just storm chase, as it were, with a ship and be like, that's raining over there, I want to go over there. You really just kind of get whatever the ship is sailing under. And in a lot of times the ship is actually stationary, and so you're just capturing what's on there. So the nice thing about the ocean rain data set is you kind of use it more statistically. So you're getting a sample of a lot of different types of things as these things sail around the oceans, and not necessarily, trying to capture exactly what's happening within that one cloud that moved over the ship. But that's a great point. Thank you.
Yeah. And there is another question for Elinor. As computational power improves year after year, is there a future where sub-grid scale processes like convection are resolved globally without the need for parameterization? Or is this too much to ask?
I think that is in the future. How near that is, I don't know. There's a lot of discussion of how quantum computing could potentially be useful for this kind of thing, but it's not asking too much, but it's not in the immediate future, I would say. There's also interesting challenges that a lot of convective parameterizations were written for climate models when they were 300 or 400 kilometers in size, and they're still using the same ones when they're 100-kilometer grid sizes. So there may be like issues that parameterizations don't scale in the way that they should. So there's a lot of interesting questions kind of still out there on parameterizations for sure.
Okay.
Yeah, the first quantum computing climate model will be very, very interesting.
Yeah, I have to
Looking
say
forward
I don't really understand it, but I know it's a thing and people
Wow.
are talking about it.
Very interesting.
Okay, I think we're already to the end of the hour. Just before closing, I want to quickly ask all the speakers, what kind of suggestions do you have for ECSPrecip? This is Shruti's question. What kind of suggestion you have for early career students or postdoc who are starting their career? What is the major gap in each of your fields? Just a quick.
Okay, I'll throw in my thoughts. There are a few things. So first of all, the algorithms are still continually improving. So we are always looking to, try and come up with better satellite estimates. I talk about the various approaches. They still need, and especially these days with machine learning algorithms being sort of the new thing, that there is a lot to be done there. And then there are also other aspects that need to be, we really need to crack, such as snowfall. I think we talk about satellite precipitation, but most of the time it's rainfall. Snowfall, we're still very lacking. And also uncertainty quantification. This is a long-standing problem, and it still is. And also, perhaps the last thing I'll throw out there is what's sometimes at NASA called level 4 products, which are observations combined with models, and not just on a superficial, like I'll choose this or that level, but integrated in a way that produces the best of both worlds. And that's it for me.
Brenda, a quick statement.
Yeah, I'll jump on to what Jackson said there. I think, well, I'm just going to say two things. One is that, yeah, definitely start thinking about uncertainties and quantifying the errors in the observations too. I mean, like I said, it's retrieved. We have all these different methodologies, understanding the errors in what you're getting is really important. And just, there's a lot of field project data out of there. People, it's like an unmined, untapped gold mine of data that just sits out there. And we really are just now, I think, coming to the point where we have the computational power to start looking at this in more of a holistic sense. And so I would encourage people to just use the field campaign data that's out there towards the goal of, any scientific question you might have related to precipitation. There's just so much data out there. So.
Yeah, there's plenty of data in the model world too that can be used. So uncertainty is a challenge both in current conditions and especially for the future. I would say certainly extremes are an area that are really important to understand, both wet and dry. And then also going beyond just why are models different than observations, but trying to understand like, why are they different? What are the processes that are occurring? And that's where really you can start using observations and field campaign data to actually try and answer some of the why questions. The other point is it's important to understand is what information is useful from climate models for people who are making decisions. So typically as scientists, we're not the ones making the actual decisions on the ground. So what do city planners and reservoir scientists and what do they need? And how can we bridge that gap between us and users of this information?
Yeah, thank you all speakers for your time to putting this presentation together and the detailed presentation. I will now hand it over to Shruti if she has anything to say.
Yeah, I just want to thank you all for this amazing talk and great suggestion. I'm sure everybody has got very useful information from this. And we recorded this session and we'll post this on our website. So if you have any more questions, you can reach out to speakers or you can reach out through us. I have posted our social media links and mailing list subscription form if you are interested. Thank you so much, everyone.
Thanks everyone for joining.
Thanks everybody for joining and everybody for organizing.
Yeah, thank you so much.
Yep, thank you.
Thank you. Bye.